Have you ever thought of a question or a problem that struck you as particularly interesting and gave you a desire to find the answer to it or to see it through to the end? This is my story of a journey that I recently took to solve one of these types of problems and what I've learned from it. The problem starts with polygons. I'm sure many of you recognize these shapes. We teach our kids from an early age to answer, what is this shape? What is that shape? They can tell the difference between a triangle and a circle and a square. You've seen these before, probably a pentagon with 5 sides, a heptagon with 7, a dodecagon with 12, and the hecto might as well be a circlegon with 100 sides. These are all polygons, and moreover, they're regular polygons. A regular polygon has sides all of the same length, and they're convex, meaning that they kind of cave inward toward themselves. Their interior angles are all less than 180 degrees, the angle between this side and that side. Now, you might be asking, why do we care about polygons, right? Well, what's kind of special about this? Well, I did just say, we see them all the time in school, right? We talk about, polygons and their properties. You see them in math classes from all the way back to kindergarten up through high school. And like many questions or problems that you might have thought up, this was born out of boredom. Like many high school students, my friends and I were frequently bored in class. And like many typical high school students, we would typically doodle or draw on our notebooks or desks or what have you. And, in math class, one of the things we drew were polygons, draw shapes because it's fun. But we started drawing these shapes that look a little bit like this. It's a polygon with all of the non-adjacent vertices connected to each other. Makes these cool star-looking type things. And they do look pretty cool. You can see the pentagon here. This is an octagon, nonagon. This is a n equals 15 polygon. And here, n equals 31 and 32. So they look like pretty cool shapes, right? But that wasn't the first thing that interested us. The thing that really interested us is how many areas are formed when you do this procedure on a polygon by drawing these lines. You can see here for the pentagon, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 areas formed by those lines. Octagon, you can tell, there's quite a lot more. Same thing with the nonagon and so on and so forth. And so, being students that are interested in math, we set out to try to solve this problem, see if there was some formula or some series representation that we could find to tell us the number of areas in any polygon. Well, we tried and we tried, but we quickly found out this was a much harder problem than we initially thought. The real crucial thing is the fact that it's really difficult to draw these once they get to any level of complexity. I mean, even the octagon isn't the most simple shape to draw. Go ahead and try to draw an octagon with all of the sides being the same length. And then you have to go ahead and connect all of those vertices. The problem arises is when let's look at the n equals 15 polygon here. Look and see how close some of those lines come to each other, but they don't cross. So the difficulty you find is that sometimes the lines do indeed cross, and sometimes they don't. And that determines whether or not there's a little area there, or there's not. And we quickly found we couldn't draw one of these accurately above, I think we got up to maybe n equals 11 or n equals 12 in terms of the polygons. So this is going to be clearly a much more difficult problem to solve. We didn't have very much data to work with, but we did what we could. We found all the areas in the polygons we could draw, and we just could not find a representation. Well, like many high school students, we had lots of other interests, and so we quickly moved on from finding this problem. But I thought of this the other day, and I was thinking back, and I thought of this problem, and I was like, I probably can solve this now. I had some experience in college with computer programming, and I realized that a computer can draw these so much better than any human possibly could, right? Humans can't draw perfection, but computers can do, at least near enough as it doesn't make any difference, can draw a perfect polygon. You can see all these images here are all drawn by a computer program that I've made that goes ahead and draws these polygons, connects all the vertices, and even counts all the areas inside. Because, of course, the counting gets a little laborious after a while, and so we might as well make the computer do that. And so that's the journey. And hopefully, we're going to find it and solve it to the very end. So the first thing that I found that I wanted to analyze was the number of lines that you draw for each polygon. Because we're going to find a formula for the number of areas eventually. At first, maybe we'll just try our hand out and try to see how many formula for the number of lines that you can draw. So here's a table showing you the number of sides, n, versus the number of lines. And you can see that they don't grow too fast. There's not too many lines. You get up to 464 here for a n equals 32 polygon. And some of you might have already even spotted the pattern that you can see in these numbers. I didn't see it initially. But I wanted to have kind of a better method anyway for use later, so I looked up some methods that people use to find formulas or a series representation for a given sequence, and the method that I kind of settled on was the method of differences. How you use this method is first, go ahead and just write the list of numbers, the list of n's, the input value that you would have, in this case 3, triangle, 4, square, and so on and so forth, the number of sides, and then your function that you're trying to find, the values of that function. For example, here, for a triangle, there's 0 lines that you can draw. For a square, 2, pentagon, 5, and so on and so forth. And what you're going to do is you're going to find the differences between each successive pair of numbers. So for example, between 2 and 0, difference is 2. 5 and 2, it's 3, 9 and 5, it's 4, so on and so forth. What you're doing is really kind of finding an approximation or a representation of the first derivative of n, for those of you who have taken calculus before. So you can go ahead and do this, and voila, we see something that looks good, right? This is clearly a pattern. Each one of these is increasing by 1, right? And so if we do this again, which is akin, of course, to finding a representation of the second derivative, we find that it's a constant. And for those of you who do know the calculus, if the second derivative of a function is a constant, what kind of a function do you think it is? You probably should immediately think of a second order polynomial, something that's x squared plus something plus something. Here we're going to use n as our variable instead of x. Method of differences, every time you find a difference, you add 1 to the order of the polynomial. Since it took us twice to do this, we know that we have a second order polynomial here. And so that restricts us to only have to finding 3 numbers now, a, b, and c. To do that, again, there's probably many methods you could use. The method I found that was probably the easiest and the one that's the surefire method is to write a system of linear equations here. For the triangle n equals 3, if you plug in 3 for n, you get a times 3 squared plus b times 3 plus c, and we know that because there's 0 lines in the triangle that has to equal 0. You can do the same thing for n equals 4 and the same thing for n equals 5. Once you have this system of linear equations, you can set up a matrix equation. Put all the values you know in a matrix, multiply that by this 3×1 vector here with your unknowns, a, b, and c, and that has to equal the resultant vector, the 0, 2, and 5, the number of lines that there are in each of those shapes. And so we were going to use some linear algebra here to solve this here. If you have some matrix A you do know, times a vector x you don't, then that equals some resulting vector b. You can just take the inverse of A, multiply it by the matrix B, or the vector B here, pretty much the same thing, and you're going to get your vector of unknowns. Now, it's been a little while since I've taken linear algebra, and the main thing I took from that class is I never want to do matrix multiplication or taking the inverse of a matrix by hand ever again. So we're just going to go ahead and use a computer algebra program or even like a TI-83 calculator to go ahead and solve this system here. Just put in the matrix, take the inverse of it from the program, multiply it by b, and we're done. Out of that, spits out an answer. We get that the vector x is 1/2, 3/2, minus 3/2, and 0. So those must correspond to our numbers a, b, and c. Plugging those into the formula that we'd written earlier, we have an equation for the number of lines. It's 1/2 times n squared minus 3/2 times n, and there's no constant term because c is 0. So great, this is a pretty good method, right? Pretty easy to use, very straightforward, not bad, and we can see that it definitely works. If you pick your favorite graphing program and graph the number of lines versus the number of sides, you get a figure that looks something like this. The blue dots are the empirical values that we found from the program up through 32. We can fit a curve to this, and lo and behold, we get the same numbers. Note that the C here is a little off because of just computer rounding. 6.49 times 10 to the minus 14th is pretty much the same thing as 0. So great, awesome. The next step is to make our program be able to now do something else. Now, that something else, though, is a little interesting, right? So what's the next step, probably, in finding the areas? We've got these lines drawn for our program. What I first thought of was, well, maybe we can count the number of times that those lines intersect, the number of interior vertices there are in this shape, the number of intersections there are. And so, after much labor, I got the computer program to do that for us, and here it's plotted those intersections, mostly just for visual inspection. It's nice that you can see, hey, the computer's put a green dot at each one of those intersections. It's not off. It's not misidentifying intersections or anything like that. Plus, it makes for some nice visuals for us here. So, looks like the computer's worked. It's shown that there are 5 intersections of vertices inside this pentagon here. We can do the same thing for the octagon. And this one is the 15-sided polygon here. As you can see, this kind of highlights a few of the problems we were having. Number one, it's just really hard to count all of these manually, right? There are tons and tons, over 1,000 intersections in this shape. That would be difficult to count and keep track of. And number two, you can see a lot of the intersections are clustered very close together, right? There are, almost like a dozen intersections just right there. How would you be able to tell, if you were drawing this by hand, what was an intersection and what wasn't? So that's why the computer was born, and that's why we went ahead and did the project like this. So, like we did with the lines, we can go ahead and construct a table with the number of vertices versus the number of sides. This grows quite fast, much, much faster than the number of lines did. But no matter, we can still use our same algorithm, the same method that we used previously to go ahead and try to find a formula for the number of intersections, number of vertices inside these polygons in terms of n. So we'll do the same thing. Go ahead, we have our list of n's and our list of values, the number of intersections. Go ahead and find the first differences. But already you might see a problem, right? Look at the first differences. 1, 4, 8, 22, 14, 77, 35. It goes down. Now that's interesting. Well, let's find the second differences. Now we got some negative numbers in there. Third order differences, even more negative numbers, they're getting worse. If you carry this out, you're going to find that you do not get down to a constant. So something's up, right? There's some problem here. Now, you might have already realized, just by looking at some of the pictures, and I'll go back and let you look at these, that there seems to be a difference, right, between the odd ones, this is n equals 15, and the even ones. This is something we even recognized back in high school, that we thought there might be 2 different formulas, one for the odds, one for the evens. You notice the evens have a circle right in the middle of the polygon. The odds do not. So that's interesting. So we can see that even further if we go ahead and graph the number of intersections versus the number of sides. This clearly does not look anything like the graph we saw for the number of lines, but on closer inspection, you might notice that the values that look weird, the ones that are kind of below everything else, right, all correspond to even numbers of sides. You got 12, 14, 16, 18, 20, 22, 24, so on and so forth. Those ones seem to be the problem, not the odd ones. Those look pretty good. So maybe that's our next method of attack. Let's isolate only the odd ends, take their values, and go ahead and apply the method of differences to them. Find the differences between all those. Looking good so far. Okay, it's not second order, but it's still looking good. We're getting down to something, it seems. Do the third order. Looking great. And voila. We get a constant difference. So for the odds, there does seem to be a function we can do. And so thing here now is that it's not a second order polynomial, but it's going to be a fourth order polynomial. So now we have 5 different numbers we have to solve for, a through e. It'll take a system of 5 linear equations, so we're going to use a matrix that's 5 by 5. Just, again, very similar to the one that we used before. Solving this matrix equation using our computer algebra program, we come up with a formula. It works. Number of intersections equals 1 over 24th times n to the 4th minus 1/4 n cubed plus 11 over 24 n squared minus a 4th n. And again, there's no constant term there. So great. We've solved, it seems, half of the problem, right? But what about those even ones? What about those? This is a graph of just the even ones. It does not seem to be any pattern there. If there's a pattern, it's going to be much more complicated than what we've been looking at so far. So, like any good person, I decided to move on from here. It looks a little complicated here, and the point of the program, after all, is to count the number of areas, right? So let's go ahead and finish that first, and then we can come back to this odd versus even thing. Maybe it'll work it out for itself. So let's go back to our pentagon that we've been looking at so far. And now let's make our program magically count the number of areas. And ta-da! After quite a lot of work and a lot of frustration, I was able to fairly successfully get the program to identify and count the number of unique areas in all of these polygons. Here, for visual effect, we have the program plot a little pink or purple dot in the exact center of all the areas that it finds. That way we can correctly correct the program if it isn't finding the areas correctly. And again, these make some pretty beautiful looking images. Here is n equals 15, a really cool looking pattern, almost like maybe like a stained glass window that you would see somewhere. So kind of cool, but that's not the issue that we're looking at, right? We're looking to find and count those number of areas. And so again, we can count those using the computer program and fairly successfully make a table just like the ones we've seen before. I will note the computer program isn't perfect. After about n equals 30, the program starts failing out due to some rounding errors and just general, this is a lot of stuff to do for the program. So it gets a little difficult. Didn't find one for 30 and 31 accurately, and above 32, there was pretty much no hope after that. Plus, it took a while once you get to that high. But no matter, we've got a lot of data here, much more than we had in high school. Probably only had 12 through 3. So maybe we're going to be able to find the formulas from this. So we know the odds worked for the intersections. So let's go ahead and do the odds for the areas, and lo and behold, it works. Use the method of differences, solve the matrix equation, we get a formula for the number of areas for the odd ends. And interestingly enough, it looks very similar to the number of intersections, right? The first two coefficients are exactly the same. And this one changes by 12 over 24, and this one changes by 6 over 24, and we've added a constant one at the end there. So this tells us two things. Number one, it tells us that we were right. The number of intersections is very related to the number of areas. It was a good avenue to go down. Of course, the second thing it tells us, which is bad, is that this is probably not going to work for the evens because these seem to be very related concepts. And indeed, you would find that that is true. It is very difficult to find a sequence or some type of series to describe the even ones. This is, again, just the graph for the intersections, but you would see a very similar graph for the areas. Okay, so you can try to look up a lot of different methods. It seems to be getting difficult and a lot more complex than we probably can do. And one of the best things you can do as a scholar is admit that you don't know and go ahead and try to go do some research. And so that's what I did from here. Went and did some research and found, maybe unfortunately, that somebody else has solved this problem. So we weren't the first ones to think of this, but now we get the answer at least. So paper by Poonen and Rubinstein published in the Journal of Discrete Mathematics, they solved this problem. Though, I will say in our defense, not too many years before we were coming up with and solving this problem back in high school. They only did this in 1998, using a computer program, no less. So, to summarize here, this is an extract from the paper showing their theorem 2. There are a function of n. That's a function that shows the number of, they call them regions, I call them areas, number of regions in each polygon. You notice here, they don't have a restriction. It's for any n greater than or equal to 3. So, any polygon, it's a triangle or greater. And they don't make a distinction for odds and ends. Odds and evens, my apologies. So, you can see this formula is quite complicated, probably much more complicated than something we were going to come up with to help us define are polygons. But one thing you might notice is the first part of their equation is exactly the equation we found for the odds. Now, here's where a little explanation comes in. What are these delta things here, right? You can see a lot of other polynomials and these deltas. They're very similar to a Kronecker delta. If you've ever dealt with quantum mechanics or seen those before, these deltas can either take on a value of 1 or 0, depending on the input. This input they're putting in is n, the number of sides in the polygon. The other number they have is that 2. They're going to call that number m. And for those of you who've done math or computer science, what this function simply does is take n mod m, and if that is 0, then it's going to go ahead and return 1, and if it's not, it returns 0. What that means is if n is divisible by that number, 2, 4, you can see 6, 12 in there, then it's going to go ahead and return 1. If it's not, then that thing is 0 and those terms don't matter. So this is where the even terms go. There's a modification. If it's even, this is going to trigger and it's going to be 1, and we have to make a modification to the polynomial up here. And so this is the explanation. This is why we have to modify this polynomial for the even ones, why it doesn't work. But there's something a little deeper in here. A little deeper, and we might have found it ourselves if we looked a little bit closer at these pictures. I will admit I might have and should have probably seen this as I was programming. I ran into a problem that I now suspect is very related to this fact. See, when I first made the program to count the number of areas, it worked for all of the odd ones, but didn't work for any of the even ones. And why is that? Well, look at the differences between the odds and the evens. Not just at the center, but look at all the intersections. If you go through here and look at all the intersections in this one, this is the 11-sided one, you'll notice that none of the intersections have any more than 2 lines at the intersection. No more. Whereas if you look at the n equals 12, the dodecagon, that's clearly not true. This intersection right here has 4 lines going through it. This intersection here has 3. And we could probably look at all the pictures from, n equals 3 through whatever, but they've already done the work for us, and they've actually come up with some rules. The max number of lines there can be at any intersection besides the center of the polygon, if it's odd, is always 2. It's always only 2 lines. Hence, why it was pretty easy to go ahead and find all the areas for those ones, and why my program worked almost instantly for that. For 3, if I will find 3 lines, if n is even but not divisible by 6, 5 if it's divisible by 6 but not 30, and 7 if it's divisible by 30. And there's 2 exceptions. If it's 6, you only find 2, and if it's 12, the max is 4. So this is quite complicated, and if you go ahead and read the rest of their paper, I posted the information, the citation on that. They go through and rigorously prove all of these rules that they've generated for this. I won't do that for you here. But I'll show you that we might have even should have recognized this, right? I mean, look here. Look at the numbers that don't seem to fit a pattern in the evens. 6, 12, 18, 24, 30. Exactly those numbers that they identify as being problems. And so this is the answer for us. This is the number of areas as a function of n, what we were trying to find all those years ago. And though we probably would not have stumbled on this, even if we had a lot of time to work on that problem, it's still interesting, and I think we've learned a lot here. So thank you all for watching. I hope I inspired you to go out and solve your own problems, whatever they may be. If you have any questions or anything, please feel free to message me here at my YouTube channel or at my email account. All the images you see here were generated by my Python program, written in the programming language Python. All the images are generated in matplotlib, which is a library extension commonly used for Python. So thanks for watching again, and have a fantastic day.